Okay.
Okay, this is lesson 12. This is on an RC circuit, and at the end of unit 1, the last lesson there was lesson 7, and we did do or talk about an RC circuit there a little bit. I gave you some graphs and explained a little bit about what happens in a capacitor. You actually did the experiment part with a capacitor and a light bulb, and you could see the effect of the capacitor. Now, most capacitors are not that large. That was a 1 farad, and a 1 farad capacitor is rather large. So if we want to look at or study this charging and discharging process, then we're going to need something different than the light bulb and the 1 farad capacitor. Also, at the end of lesson 7, I talked about an RL circuit, a resistor and inductor, and that's going to be in lesson 13. I will sort of tell you now that the lesson 13 is going to be very, very short. You're not going to actually do an experiment with that. We've had some, you might say, technical difficulties, and things don't always do the way we want them to. At least they don't do what we want them to on paper. So we're still going to have a lesson on it, but it's going to be a rather short lesson, and it will look at how the RL circuit compares to the RC circuit. So this one, with the RC circuit, we're going to do two main things. The first thing is we're going to look at finding or experimentally determining the time constant. And as was mentioned in lesson 7, the time constant is the product of resistance times capacitance, and if you look at all of the fundamental units of that, it does turn out that that is units of time. So here in this lesson, we're going to look at what's called a transient current in an RC circuit. If you remember with the capacitor and the light bulb, when you closed the switch, the light came on and then it faded out because the current was there to begin with, and the current disappeared as the capacitor became charged. So transient means that it exists only for a short period of time. Sometimes the transient currents we don't really worry about because they're only there for a short period and then gone. But there are some times that we do need to worry about them. But right now we're going to look at how we find the time constant for a circuit that has a resistor and a capacitor, and these are going to be significantly different in size from the light bulb and the capacitor that you had. So there's a place to draw a graph on page 103. We're going to look at just the general shape of it, and this is what was in lesson 7. So as a function of time, the voltage across the capacitor. Now we can look at voltage and we can look at charge, and we can also look at current. So we have to keep track of what it is that we're considering. So we're going to look at voltage, and for a capacitor, when you close the switch, it begins to charge, and it will charge up to some maximum value. And remember that for a capacitor, the maximum charge is capacitance times voltage. Now, we aren't going to use that in any of the things that we do today, but I just thought I would mention it. So this here is VC max. It's the maximum voltage across the capacitor, and this graph comes up and across something like that. And this is for the charging process, and then we have the discharging process, which I want to draw the graph there, so I'm going to erase that. So we have the discharging process. So after the capacitor has charged, then it's going to discharge. It's going to start here at a maximum voltage, the same that it had over here, and then it will decrease down to 0. So that's as a function of time. So we have our voltage as a function of time, and this is for the discharging process. So what we did here in lesson 7 was using power supply, so it was direct current. The current went in one direction, and that was all. Now, we're going to do something a little bit different. We're going to think about having a circuit connected to an alternating current or alternating voltage source. And the idea is that the current will go one direction, which means that the capacitor will charge one way, and then when the current starts going the other way, the capacitor will discharge and it will actually charge opposite of that. So we're going to coordinate and get all of our resistor, capacitor, voltage, and frequency coordinated so that we can actually measure something on our oscilloscope. Now, before we do that, we need to look at what's going to happen. So if we superimpose a square wave, we know that we can get a square wave on the oscilloscope. So we can think about superimposing our charging and discharging processes onto a square wave. So I'm going to draw a square wave somewhat underneath where that one was. And this is on page 104 in the top box there. So we would just have this charging up like this, and then it will discharge something like that. So the problem then is to get our square wave to have the right frequency to go with our charging and discharging processes. Now, we actually in here it talks a little bit about this, that the general idea is that it's assumed that the charging process is complete after 5 time constants. Actually, the graphs are exponentials, so theoretically the capacitor never gets totally charged, but for all practical purposes it does. And that generally happens after 5 time constants. The capacitor also discharges, and we say it's completely discharged after 5 time constants. So if we look at our square wave, starting with here, this is the beginning of a period. So from here all the way over to here is one period of the square wave, and that will cover our charging and discharging processes. That's what we want to happen. So if this charging process takes 5 time constants and the discharge is 5 time constants, then the frequency of the wave must have a period of 10 time constants, or at least that much. So I think I have, toward the end of this, there's a calculation where you have to calculate what frequency you would need to measure the time constant for a particular resistor and a capacitor. Now, the thing that we can measure, though, is at 1 time constant, which is, and I'm going to get my red pen, red marker. At 1 time constant, when t equals tau, which is RC, there are certain values that occur. So if you go back to lesson 7 and look at the equations, which are beside the graphs, and if you put in for t, if you put 1 tau, then 1 over 1, or 1 tau over tau gives you 1. And you have e to the minus 1 in the equation. So if you evaluate that equation, you will find 2 things. And it doesn't matter what values you have, if you're at 1 time constant, then the voltage, and I'm going to put a subscript tau. So this means the voltage at I know what I need to do. Write it this way. This is the proper way to write it for a function. So the voltage at one time constant is going to be 0.63 times the maximum. So if you evaluate the equation at t equals tau, you will get a coefficient out here of 0.63. So what we're going to do is to look at 0.63. So we have about a half there, 0.63 is up here a little bit. So we're going to go over here and say that this is 0.63 Vmax. And then we're going to look down here. Remember that on the oscilloscope, the horizontal axis is time. So if we find our 0.63 Vmax, go over to the graph, go down, then this is going to be the time constant. And that's essentially what we're going to do, is to, we'll get this pattern on the oscilloscope, and then we'll actually measure the time constant for our circuit. Now, this is for charging. I should put here charging, during the charging process. During the discharging process, it's a longer word, the voltage at one time constant is 0.37 times the maximum. Now I'm talking about voltage here because on our oscilloscope this vertical axis is going to be voltage. It also happens that it's related to the charge and also the current. But what we're going to do now is just look at these voltages. So if we go to our discharging process and go to 0.37, that's about a third of the way up, and go over, and if I had drawn these right, exactly, then this would have been one time constant. It's not a whole lot different. So this one is 0.37 Vmax. Okay. And we've already figured out a resistor and a capacitor and a frequency and everything that will work nicely. So you don't have to try to figure out what to use. Okay, so that takes us to part 2, which is measuring the time constant. Before we start looking at the oscilloscope and the circuit board, there's one more picture that I want to draw, and that is on page 105 at the top. It says to draw a circuit showing an alternating voltage source, a ground, a resistor, a capacitor, and a voltage out for the capacitor. Now, if you remember, or perhaps you might want to look back at the end of lesson 6 when we talked about a voltage divider. So we're going to be referring to that that form of circuit in a couple of these lessons. So with our voltage divider, the format is, I'm going to start down here with ground. Ground is usually about 3 or maybe 4 horizontal lines, equally spaced, but different lengths so that they form a triangle. That's just the standard symbol for ground. And that's what's in the lower left-hand corner of the circuit board. So we're going to draw a line up here. I'm going to draw this with a wavy line there. This is the voltage in. That's our source. And when we do this on the circuit board, that's going to be our function generator. We generally just draw a little wavy line there regardless of what shape of wave we actually have. Even if we have a square wave, I suppose you could put a square wave there if you want to, and that would be fine. But the easiest is just put the wavy line. That means an alternating source. Okay, then we're going to go on up a little ways, over and down. And then we're going to have a resistor and a capacitor. Now what we want to do is to be connecting across the capacitor so that this format or this picture is what we see. And remember that the capacitor, or whatever we measure, the voltage across whatever we measure, must be connected to the ground position. So this bottom position here, and before I mentioned calling it the measuring position, because we want the ground of the probe on one side and the probe hook on the other side, and we cannot have ground in more than one place. So all the grounds have to be connected to the same place. So if you want to measure something and you're using one side of it as the ground, then it must be in this position. So we're going to put it here. I'm going to put C here for capacitor. We'll put our resistor up here, all that R, and then we want the voltage across the capacitor. That's our voltage out, or what we're going to measure. So the standard terminology is to call it voltage out. Now, one thing you want to kind of keep track of, you don't want to think of voltage in as a voltage going in like a current goes in. That's not what happens. And voltage out is not a voltage going out like current. Voltage out means that you're measuring across something, and basically that's what you're measuring. And the voltage in is what's there to begin with, and that's what's driving the circuit. So the standard thing is to put two little lines here with the open circles here, and we're going to call this voltage out. I am going to subscript it with a C and then put out. At this particular point, if the voltage across the capacitor is all that you're going to measure as voltage out, you would not need to have the subscript C. But in the next part of this same lesson, we are going to be measuring the voltage across the resistor, and when we do that, we will have to move the resistor to this position. I don't think I have a place for you to draw that circuit, so I suppose you could if you wanted to, but I will make sure that we mention when you do that. Okay, so this is at the top of page 105. The next part of this is telling you how to connect everything to get ready to measure this. So while Adrian is moving the camera, I will go around the table here. Okay, so that's about right.
I think so.
Okay. So I still have the oscilloscope here, the circuit board, they're plugged in. I have both of them turned on, so I have this nice little green line here. And then what you're going to need is a little black wire and a red wire. I use red and black. Doesn't really matter. The circuits really don't care what color the insulation of the wire is. So this is ones that I've used before, so if you've left your thing connected, you might just still have it there. And then we're going to use a capacitor. It's a different capacitor. It's a 103K, so it's the small one. And we're going to use a 10K resistor, so it's brown, black, orange. Now, I normally start from the ground and build my circuit. So we're going to start here with the ground wire, and it needs to be in one of these positions down here next to the outside casing of the ground. And then I'm just going to put it over here somewhere, it doesn't really matter where, on the circuit board. And from our picture, we have the capacitor next. And for this capacitor, it does not matter which end you put next to ground. Some of them, it does matter, but this one does not. So I'm going to put that one in there, and then the other end of it up here a little ways. So you have to make sure when you're doing this, sometimes these come loose, or they tend to come kind of work their way out of the circuit board. Okay, then I need my brown, black, orange resistor. I'm going to put it kind of next to that, and then have it up here somewhere. So this should look just about like the one that you did in the other two lessons, except you have a different resistor and capacitor. Now we need our wire to finish our connection, finish our circuit. So we have from the same row that has the resistor up to the function generator. Make sure it's in one of these over here under the function generator, not under the TTL. Okay? Now I have actually set some of these about where they need to be, so it wouldn't take quite so long to do this. I'll go through that to make sure that you understand where all the knobs are. So you need to have the function generator set to the square wave. So we have the function, this one down here. The square wave is the right position. And let me put this here. The frequency knob to 1 kilohertz. So up here, make sure that you look down. If you look at the side, you may get it in the wrong position. It needs to be at 1K, so that's 1 kilohertz or 1,000 hertz. And then the frequency dial to about halfway. So what it's going to tell you in the next step is to adjust it to a frequency of 500 hertz. Now there's several ways two main ways you can do this. You can use the orange meter set at the frequency position connected across here, and then change the dial here until that does say 500. The other way is that if this is on the 0.2 milliseconds, then you need 5 divisions, either 5 or 10 divisions. So I've got it set here, so we'll see in just a minute. But the other thing is, if this knob is set at 1 kilohertz, then 500, of course, is half of that. So the variable dial here should be just about in the middle. It shouldn't be really one way or the other very much. Okay. Now, we don't see anything here. Oh, I have to change this, and before I get this posted, I will change this. We need to have our oscilloscope connected to our function generator, or we aren't going to get anything. So we have the ground clip, which is the alligator clip, connected to the ground side, and I say connect it to the capacitor that's grounded. You could connect to the ground wire. You could actually connect over here if you want to, but I usually connect there because that's more like what I'm thinking about. I'm measuring the voltage across. So then the clip needs to be connected to I need another step in here. Okay, this needs to be connected up here so that we have our square wave. Okay, now if you notice, this is on 1 volt per centimeter. I've already adjusted the amplitude to get 2 volts peak to peak, so it's 1 volt above and 1 volt below the horizontal axis. And then if I move this, position this just a little bit, then we have 1, 2, 3, 4, 5. So this is half of the complete period. So there's 5 of these, and I would have 10 of those for 1 period. So that's the period. We have the frequency, or 1 over the period, so 1 over, I don't do this in my head very well. Okay, 10 times this, 1 over 2 milliseconds. So I think if you do that, you end up with 500 hertz. Okay. So now we want to connect, to move our probe hook to the capacitor. So I'm going to move it down here to the capacitor. And you can actually connect either to the capacitor or to the resistor wire that's in that same row, because that's actually the same position. Okay, notice that we have a couple of curves, and we're going to move some of these a little bit, so that we have a decreasing one and we have an increasing one. You can move the trigger level just a little bit, and it will get it. Oh, if it does that, that's too much. You can get it where you have most of an increasing and most of a decreasing there. Now, if I were to change this to the 0.5 milliseconds, then I can see I have a lot more of those. But the time will not be as accurate because it's on a larger scale here. So if we haven't put it back to the 0.2 milliseconds per division, then it's easier to get a good reading there, good value. Now, there's a technique for doing this. So the idea is that we want, since from peak to peak is 2 volts, then at our one time constant, the voltage should be 0.63 times 2. So if you multiply 0.63 times 2, you should get 1.26 volts. So what we want to know, and there's a way of doing it, we want to know if we go up 1.26 volts, then how much time is it over? So what we're going to do is, and when you do this, you need to position this very carefully. I needed to change the trigger a little bit so it's not wiggling. Okay, position. We want to position this horizontally so that that corner is at the intersection of a vertical and horizontal line. Now, it doesn't have to be right there in the middle. It could be at any of those, because you're going to count squares, or count. So we're going to want 1.26 volts. So up 1.26 volts, there's 5 of the little divisions, so a little division is 0.2. So just a little bit above one of those little divisions above the big division. It's not that easy to look at that and go over and measure. So what we're going to do is we're going to move this graph to the left until the 1.26 part is there on that y-axis. So if I move this over to the left, so that, and I should have shown you this on the board, but I didn't think about it then. If you move it to the left so that the graph crosses the y-axis just a little bit above the 1.2 position, then you know that from this vertical axis back to this corner is the time. Well, it's not that easy to read that there, so we can move it vertically. Be sure you're moving it vertically, so we can move that up. And then you can read the time from the vertical axis back over to that corner. And read it as carefully, probably more significant figures than someone would say you can do this. Each of the little divisions is 0.2, so you should get as good an estimate or good a reading as you can. And then that is the number of centimeters. So I would say roughly a half a centimeter, maybe 0.4, 0.5, something like that. And then you need to multiply that times the time per division for your time scale. So if we had 0.5 here times 0.2, that would be 0.1, and this is milliseconds. So that would be about 0.1 milliseconds for the time. And that would be the experimental value for the time constant. Now, on the next page, you're going to do this again, except you want to do it for the discharging process. So we do the same sort of thing. We move this over, and you should make sure, mine's a little bit higher than 2 volts. Make sure that it's just really right there, whatever this is, and then up 2 centimeters. So we're going to move this over, and we're going to start with it here, and I'm going to move this down just a tiny bit. Okay. Now, we need the 0.37 or 0.37 times 2 volts. That is 0.74. So we need to be up 0.74 volts from this bottom line here. So that's almost 0.8. So I'm going to use the same technique. We're going to move this, oh, wrong direction, until the graph crosses the y-axis about 0.74, so a little bit below 0.8. Okay, so then from the y-axis back to this corner is the time that we're interested in. So now we're going to move it down to the middle axis that has all the little lines on it, and then you can make that reading. So again, it's about 0.5, maybe a little bit more, a little bit less, and we still have it on the same time setting, so that would give us the same time. And then the next few statements or steps are to actually calculate the time constant and find percent error. So basically, that's how you find the time constant. But the crucial thing is that you have a resistor and a capacitor and the proper frequency to go with it. Because I tried several others and you can get some really strange things. But this does work very nicely. Okay, so the next part of this, and I maybe should have talked a little bit more about it, but that's okay, is on a low pass or high pass filter. So we don't know yet what a filter is, but we're going to find out. So it tells us here, there's some theory there. You should read through the theory. I think it explains things fairly well. Then we're going to use the same resistor and capacitor, except we're going to change and use a sine wave. So I'm going to change this back over to a sine wave. And I'm going to leave the resistor and the capacitor in the same position that they were. A little bit later we're going to switch the positions, but for right now we'll just leave it where it is. Now the general idea is that for various frequencies you will get out, or the voltage out will be maybe either close to the voltage in or maybe only a small fraction of that. So the table on page 108, it has the columns and they're labeled so you can tell what you're supposed to be measuring. Now, the easiest way to do these frequencies is to just change the knob up here. If you want to, you can use the frequency meter and check to see that it's exactly the 100 or 1000. I didn't really do that. So I just put it on the 100. So I'm going to change this now to 100. Make sure, yeah, there's the 100. So this sort of disappeared. So you're going to get used to changing this. Oh, I need to have this one up here. To begin with, we want the voltage across the combination, and that's what I call the function generator, the Fn. Now we need to adjust some things here. We need to get our wave so that we can actually see it. I don't have to change the amplitude because it's still about 2 volts peak to peak. I am going to position it up a little bit. And I know that right now it's flashing, and that may be very annoying. But if you change it to where it doesn't flash as much, it spreads it out a little bit more than than is convenient. So I'll just show you what you're going to be measuring. Okay, so at this point you're measuring the peak-to-peak voltage across the whole circuit, which is the series resistor and capacitor. Now, so it's 2 volts, so you would have 2. Now we're going to measure the voltage across the capacitor, just the capacitor. So I'm going to change this so that it's connected down here just across the capacitor. So if you look at that, it's like, well, that looks pretty much the same, and you're right. So the voltage, the peak-to-peak voltage across the capacitor is still 2 volts. Now you notice that if you're trying to fill this out across the row, which I don't recommend doing, but you're going to need to measure the voltage across the resistor. And remember that to measure the voltage across the resistor, we would have to switch places with the resistor and the capacitor. So instead of switching this several times, we're going to fill out those first two vacant columns for the various frequencies, and then switch the capacitor and resistor, and then go back and change the frequencies again. So this voltage was 2. Now we're going to switch it to 1 kilohertz. And notice that this speeds up a lot, so we can spread it out, and then it stops. It's much nicer to look at. So we want the peak-to-peak voltage. Since we're not measuring anything sideways, then if it's a little bit closer together, if the peaks are a little closer together, it may make it easier to measure. It doesn't really matter where you have that along in there. So we want to go back to the function generator value. So that's about 2. And then we're going to look at across the capacitor. So we move this down to just across the capacitor. I'm going to make sure all the things are still in the circuit board. And that looks pretty much about the same. It might be just a tiny bit shorter. So if you look carefully, I suppose if you wanted to, you could put this on the half, and then it would be a little more obvious if it changes a small amount. So you have some freedom there, or leeway as to how you want to, what settings you want to have. Okay, so it's like, well, that's the same thing, so what's the big deal? Well, we're going to change it again to the 10K. Now then I need to move this back to the other side of the resistor so that we have our function generator wave. Well, that's really there, so let's just change this until we get the wave spread out a little bit. Okay, we're still across the whole circuit, and that still looks pretty good. That looks about like 2 volts. And if you think about it, if we're not changing the amplitude button, then we really should have 2 volts all the time. Now, when I did it, a couple of these were just a little bit different, but so you still have about 2. Now let's look at what we get across the capacitor. Okay, so we get something that looks kind of strange. Well, let's change a couple of these things. Some of these you can just kind of change the knobs. Don't go too wild with them, but this trigger level will help you. So just change it just a tiny bit one way or the other, and it should make the wave stop. Now, since this is so spread out, I'm going to, wrong way. I always go the wrong way on those things. I'm going to change it so that the peaks are not quite so far apart. And you notice that this is definitely quite a bit less than the 2 volts peak to peak. So you can move this over a little bit, here, there, however you want to do it, and make your measurement as to how many centimeters or tenths or whatever. And then notice that this is still on the 1 volt per centimeter. Notice that the table has you recording peak to peak values, so make sure that you're doing that. So we finally saw an effect. Well, now we have one more position, the 100K, which is the largest frequency. And so, let's go back to our function generator. So that's still about 2. And as I said, that's what we would expect. Now let's see what we can figure out across the capacitor. So we move this to down here. And you might say, well, that's about 0. Well, it's not far from it. So what we want to do, oh, that doesn't help much. You can actually change this vertical volts per division, and if you get it kind of small, like 0.2 or 0.1, then you can actually see the wave. And you can count, but you want to make sure that you account for the fact that you've changed the vertical volts per division. So you should get a fairly small number there. Now obviously if we leave it on this position and go back to our function generator, it's going to be off of the screen. See, it's way off the screen. So obviously at this position the other wave was a lot smaller than this one. Okay, so that shows you what you want to measure for the function generator column and the capacitor column. Now we need to measure across the resistor. So we're going to switch places with the resistor and the capacitor. So I'll put it up here. And when you're doing these things, you have to check to make sure that things that are supposed to be in the same row are in the same row. After doing things a couple of times myself and not getting any results, I realized that they weren't in the same row. Okay, then you have to connect this back here. So this goes across the ground, and this one goes across the capacitor. So what I have now is back across the whole function generator, and we still have 2. Now as we go through this, we don't really need to do the function generator each time because we've already been through that. If you want to check it again, that would be fine. So right now we are at the 100K, and we want to find the voltage across the resistor, the peak-to-peak voltage. So let's move this over here to the voltage or the resistor position. Notice that it's just about the same. So if you're recording this, be sure you start at the bottom of the table, and then we're going to move it to the 10 kilohertz. That's spread out quite a bit, so we might change the time to get the peaks closer together. That's maybe just a little bit less than 2. It's pretty close to it, but just a little bit less. And then we change it to 1 kilohertz, and notice that we really do now have a small wave. So you can measure there and consider that with the volts per division and see what the voltage is. And then we're going to move it to 10 hertz. So this looks kind of like what we had before, except not at this position. So now we need to, okay, let's do, there we go. And there's no real way to get this to stop at this low a frequency. So you just have to kind of live with the fact that it's blinking there. So you can have this at 0.1, or you can put it back at 0.2. I think 0.1 is easier to see. And again, measure the peak to peak distance here, and then account for the fact that it's at the 0.1 volts per division instead of 1 volt per division. Okay, so that will take care of the data. There's the last column is on the voltage, and remember that the voltage across the capacitor and the voltage across the resistor are vectors. They're perpendicular to each other, and that we learned a couple of lessons ago. So if you want the resultant voltage, you don't just add the two voltages. You have the Pythagorean theorem. Okay, now this last column, I'm going to show you what is supposed to happen. Let's see, we did that. Yeah. And something that happens with electronics things, at least for me, sometimes they work, and then when I come back and do exactly the same thing, they don't do the same thing. So I'm going to show you, and it might be that you have really good luck with things, and everything does like it's supposed to do. So I'm going to show you what's supposed to be happening. I got it to work nicely for one of the frequencies. So the idea is that you know that the voltage across the capacitor and the resistor are at 90 degrees relative to each other. But then, based on the phasor diagram, if you look at the resultant, and you could do that in terms of voltages or in terms of the impedance, you ended up with the phase angle phi. So what we would like to do here is to see if we can experimentally determine what phi is. And the technique, so let me do the one that worked for me a little while ago. It was when I had the frequency at 1 kilohertz. So let me get this, okay, back to 1 volt. Let's see, I do want across, okay, I need to put this across the whole circuit. Okay, that's what I wanted. So I'm back to 2 volts peak to peak. I have my voltage connected across the whole circuit, so this is the voltage from the function generator. Now, I'm actually going to move this one. Okay, I'm going to spread it out a little bit. Now, the theory is that if you position the graph so that the center of the sine wave crosses through the origin, that's what you want to start with. And the book mentions this technique, and so I sort of just about copied a couple of his sentences. So you want to look at the shift in the zero crossing of the graph. Okay? So across the whole circuit, we have this position so that it crosses, and if you're doing this, do it very carefully. Oh, that looks pretty good. So that it crosses at the origin. Now, if I move this so that I'm getting voltage only across the resistor, and this didn't do this earlier. Let me try something here. Position that, I wonder. Oh, I know what I need to do. Okay, now then, this back here. Okay, so I've got a combination here for the trigger level so that the wave across the whole circuit, which is the function generator, when I change it to just the resistor, it stays where it was. It doesn't flicker and doesn't move. Now, what you want to notice is, what does this wave do? Let's see, I wonder. Oh, I'll just show you with this. If you look, this wave is shifted just a little bit to the left. So the zero crossing, where it crosses the x-axis, is not at the origin, but it's one little mark to the left. And that is 0.2. So it's 0.2 times 0.5 milliseconds. And I have an equation in there in step 13, so that the phase shift is 360 degrees times this little shift divided by the period. So the period is actually, you can move peak to peak. The period is 4 divisions times 0.5 milliseconds. So that's what goes in the denominator. You actually don't have to multiply that out, because the numerator is going to be 0.2 times 0.5 milliseconds. And then that quantity times 360 degrees. And that will give you the phase shift. So if you try that, and I might just try it and see if it'll work on, I don't have much hope, but okay, I'm going to spread this one out. Well, there's a qualitative something that happens. So this is at a higher frequency. So I have this crossing the zero there. Now if I move this to just across the resistor, it looks like it has not shifted. If you look extremely carefully, it might look like it has shifted maybe a fraction of one of the small divisions. But the point is here that it did not shift very much at all, and it's not noticeable enough that we can actually make a calculation. So when you're doing this, if you can get something for the frequencies other than the 1 kilohertz, that would be fine. If you can just get the one for 1 kilohertz, that's okay too. At least for the experimental part. Okay, the next page, or on page 109, there's a table there where you're going to basically use some equations and fill out and do a number of calculations. And I think I'm just going to let you do that. Now, the point of this is looking at what's called a high-pass filter and a low-pass filter. So if you think back to what we were just doing, when we have, and we're at some of the higher frequencies, oh, there's an even higher frequency. If we're at a high frequency and we measure the voltage across the resistor, it is essentially the same as the voltage across the capacitor. So with an RC circuit and with the voltage out across the resistor, that is called a high-pass filter, because the high frequencies you actually get out basically the same thing that you put in. Now, if I'm measuring across the resistor and go to the low pass frequency, or the lower frequencies, oh, my wave about disappeared, I get very little. So if I'm measuring across the resistor at the low frequencies, then, oh wait a minute, yeah, at the low frequencies, then I don't really get anything. And if you go through here, you notice that that's the opposite effect as what we got with the capacitor. So an RC circuit can be used as a high-pass filter or a low-pass filter depending on whether the output voltage is across the resistor or the capacitor. And it does, I do explain that in there, and if you think about it and look at some of the equations, I think it'll be a little bit more obvious. The end result, though, is that with a capacitor, if the current is changing direction rapidly, the capacitor does not have a chance to get charged, and if it doesn't charge, then it really has pretty much no effect in the circuit. So it's not going to do anything in the circuit. Now, I think that's about all. Oh, you're supposed to draw a phasor diagram on the next page, and you can do that with the values in the table. The thing that I would recommend, and I even say it there, is I would like for you to draw those approximately to scale. You don't really need to use a ruler and measure unless you just want to, but if you have a resistance of 10 kiloohms and another resistance or a reactance of 100 kiloohms, you know that that vector should be a lot longer than the resistor vector. So you can do them somewhat to scale. The important thing, though, will be that in both the high-pass and low-pass filter, the resistor vector should be the same length. If you don't have the same length, then you aren't going to get the proper relationship of how all those things are related to each other. So I think that's all I'm going to say. Again, we're getting into some of the more complicated things, and if you have questions about anything, please feel free to email me or call me.